Today's lecture is about divisibility tests. What we're going to be looking at is first the definition of divisible. We're going to look at some examples. We're going to see what that means both just with numbers and also with pictures. We're going to talk about the divisibility lemma and why it is true. We're going to talk about specific divisibility tests. And then we're going to prove those tests using the divisibility lemma. And then you're going to get some chance to practice all of those things in your homework. All right, our definition comes first. We say A is divisible by K whenever A is a multiple of K. In other words, A is equal to K times some whole number, little a. It's helpful also to know some synonyms for divisible. So we've got a few here. And at any point that you need to on the handout, pause, fill some things in. This is a spot to pause and fill some things in. First, A is a multiple of K. K divides A. K is a factor of A. And we get remainder 0 when you divide A by K. Now for a picture representation of what this means. We've got our algebraic definition at the top, but we're going to look at two specific examples. 36 is divisible by 4, means that as a rectangular array, we can represent 36 as 4 equal rows. So here we have 4 equal rows of 9. And then 30 is not divisible by 4, and we can represent this as a picture. We see here that we can get 4 rows, but they are not equal rows, and we actually have a remainder of 2. This is the part that is not equal among the rows. All right, now we're going to look specifically at some number examples. So first question, is 729 divisible by 6? And you should pause right here and divide 729 by 6 and see what happens. 729 works out to be 6 times 121 plus 3. So that's a remainder of 3 when you do division. So 729 is not divisible by 6. Next is 921 divisible by 3. Again, pause here and divide 921 by 3, either using long division or your calculator if you need to. And we'll check the answer. 921 is 3 times 307, so it has a remainder 0. Also, 921 is a multiple of 3, so 921 is divisible by 3. And next is 2,436 divisible by 8. Pause. Divide 2,436 by 8. See what you get, either using long division or your calculator if necessary. And we see 2,436 is 8 times 304 plus 4. So that means there's remainder 4 here. So 2,436 is not divisible by 8. Now we are ready to talk about the divisibility lemma. It's a very useful lemma that we apply over and over again. And it says, suppose A is a number divisible by K, so think A is a multiple of K. Then some other number B is divisible by K, so it's also a multiple of K, if and only if, when we add them together, we get something that is divisible by K. In other words, the sum is a multiple of K. So just a note here, that symbol with the arrow at both ends is said if and only if, and it means the statements on the left and right are equivalent. So if one of them is true, so is the other one. All right, we are going to prove the divisibility lemma. And the reason we're doing this is so that we really understand what the divisibility lemma does. And we're going to do this in two ways. We're going to do it with pictures, and then we're going to do it algebraically. We're going to go with pictures first. Every single time we're thinking about this, we are assuming that A is a number divisible by K. In other words, it's a multiple of K. So as a picture, we can represent it as an array with K equal rows. And we're going to prove that b is divisible by k if and only if a plus b is divisible by k. And we want to understand this as pictures, remembering here that b being divisible by k means that we can show it as a picture with k equal rows, if we do it as an array, and a plus b is divisible by k, we need to be able to write it or represent it as an array with k equal rows. So first, if b is divisible by k, then we can make a picture with k equal rows. So then if we add a and b together, so we're just going to take those two rectangles and shove them together and get one big rectangle, which we see has k equal rows. So that means a plus b is divisible by k. Now, in the other part of this, we're still assuming that a is divisible by k, which means we can represent a with k equal rows. And we're going to assume this time that a plus b, the whole thing, is divisible by k. And we're going to see how we can pull that apart to show that b by itself is divisible by k. Well, knowing that a plus b is divisible by k means that our picture has k equal rows. So here's our picture again with k equal rows. So to get b by itself, we're just going to separate into the part that is a and the part that is b. And so then when we look at b by itself, it has k equal rows. So it is divisible by k. All right, now we're ready to do this with the algebra. This time, instead of using the pictures, we're going to use algebra, but we are going to look at the main idea from each part from the pictures, and that should help guide us toward what we need to write for the algebra. So in this case, we're assuming that b is divisible by k. That was part one. So we can represent b as k equal rows. We can represent a as k equal rows. And then when we shoved those together, we got something that had k equal rows. So algebraically, we're trying to show that if a is a multiple of k and b is a multiple of k, then when we put them together, we still have a multiple of k. So if b is divisible by k, that means we can write b as k times little b, where b is a whole number, little b is a whole number. So notice we're doing some association here to try and keep track of things. We have capital A and lowercase a, we have capital B and lowercase b. But now we're going to look at a plus b, capital A plus capital B. So that's going to be k times little a for a and k times little b for b. And then we're going to use the distributive property to pull k out, and we get k times a plus b, little a plus little b. So a plus b is divisible by k because we can write capital A plus capital B as little k times a whole number, little a plus little b, which means that capital A plus capital B is a multiple of k. And now our second part. This time we are going to start with the a plus b being divisible by k, and we're going to pull a off of it so we have b by itself. So here's our main idea in the pictures, is that b, we got that from starting with the whole and splitting a off of it and just being left with b. So in terms of the algebra, we need to be able to say what it means for a plus b to be divisible by k, and then we're going to get b by itself by subtracting a off of a plus b. If a plus b is divisible by k, that means we can write a plus b as a multiple of k. In other words, we have k times some whole number, c. And this time we don't have a nice, cute little representation like little a plus little b we had last time. We just know that capital A plus capital B is some multiple of k. So then, to get b by itself, we start with the whole thing. We subtract off a. So we have k times c minus k times little a. We pull the k out, and we're left with k times the quantity c minus a. So capital B is divisible by k, since c minus a is a whole number. So we know that b is a multiple of k because it's k times a whole number. Okay, now we are ready for the specific divisibility tests. We're going to be looking at divisibility tests right now, just for 2, 4, 5, 8, and 10. Later, we're also going to look at divisibility tests by 3 and 9, and also 11. So a number is divisible by 10 if and only if its last digit is 0. These will probably be familiar. Divisible by 5 if and only if its last digit is 0 or 5. Divisible by 2 if and only if its last digit is 0, 2, 4, 6, or 8. It's divisible by 4 if and only if its last 2 digits are a number divisible by 4. And that includes if we had something like 0, 8 as the last 2 digits, we would still consider that to be a number divisible by 4. And for 8, divisible by 8 if and only if its last 3 digits are a number divisible by 8. And again, that would include having a 0 at the beginning. For example, if we had 0, 1, 6 as the last 3 digits, that would still be considered divisible by 8. Okay, some examples. So which of the numbers below divide the number 32,768? So we're going to look at 2, 4, 5, 8, and 10, going back to our divisibility tests that we were just looking at. So to be divisible by 2, the last digit has to be a 0, 2, 4, 6, or 8. The last digit is an 8, so this number is divisible by 2. To be divisible by 4, if we look at the last 2 digits, which is 68 as a number, that is divisible by 4. So that means 32,768 is also divisible by 4. It is not divisible by 5 because the last digit is not a 0 or a 5. And then if we look at 768, the last 3 digits, that is divisible by 8. You get 96 when you divide. So 32,768 is divisible by 8. And it is not divisible by 10 because the last digit is not a 0. So that's how we use the divisibility tests. And now we're going to go on and look at another example here. And this one is for you to make up an example of a 4-digit number that is divisible by 4, but is not divisible by 8. So to be divisible by 4, you need the last 2 digits to be divisible by 4. To not be divisible by 8, you want the last 3 digits to not be divisible by 8. So I've got an example here that I made. So 1,828. If we look at the last 2 digits, that's 28. That is divisible by 4. But if we look at the last 3 digits, 828, that is not divisible by 8. So this is an example. But you could very easily come up with an example of your own that would be different from this one. All right. Now, we are going to talk about how to prove the divisibility tests. And we're going to do this using the divisibility lemma. So the first step in this approach, we're going to use place value to break our number n into a large number, which is clearly divisible by whatever we're testing, and a test number. So for example, in the divisibility test for 5, the test number was looking at the last digit. We were checking to see whether it was a 0 or a 5. After we've done that, we are going to apply the divisibility lemma. And remember, the divisibility lemma tells us about a sum of things. So if we can put 2 parts together, then if the sum is divisible by a number, that only happens if each of the parts are divisible by the number. All right. Now, fortunately, we actually have a template for proofs of divisibility tests, and it looks like this. And this is the only place you're going to actually see these arrows drawn on here because I had to do that separately, and I couldn't do it in every place. So you are going to have to draw the arrow on there yourself. But when we prove one of the divisibility tests, We're going to start out this way by place value. Any whole number n can be written as n equal, and then we're going to get a large number plus a test number. And we're going to rewrite it as necessary depending on exactly what our test is, how it's phrased. But we're going to split it up into that first part and the test number. And then we're going to use the divisibility lemma. And we're going to say it's divisible by whatever, if and only if the test number is divisible by that based on the condition. So we'll see how this goes in a couple of examples. All right, we're going to start with the divisible by 2 test. So remember, the divisible by 2 test says that a whole number n is divisible by 2 if and only if its last digit is 0, 2, 4, 6, or 8. So we're going to follow the template for the divisibility tests, the proofs of the divisibility tests, and you guys should be filling in as you go. Pause where necessary to do that. As I go through the proof, you're going to see off to the side, I'm going to run through examples at the same time, demonstrating how this works with specific numbers. I'm going to do this with one number which is divisible, in this case by 2, and one number that is not, so you can see how everything falls into place with the steps in the proof. So first, we're going to rewrite n as 10a plus b, where b is the last digit. So what we're doing here is we are separating off our test part, in this case the last digit, from everything else. So for example, we're going to look at 214, which is divisible by 2, and 125. And this first step is to pull that apart. So I'm going to rewrite 214 as 210 plus 4. So right there, I'm splitting off the 4, that last digit. And when we do that, we know from our place value experience, that means we're going to have something with a 0 at the end, plus that last digit. Same thing with 125. I'm going to break that into 120 plus 5 so that I'm isolating that last digit. And again, we know from our place value experience, that's going to give us something with a 0 at the end, plus that last digit. And then the thing that has a 0 at the end, again, from our place value experience, we know that means we can rewrite that as 10 times something. So for 210, we write that as 10 times 21. For 120, we write it as 10 times 12. All right, our next step in our proof, we're going to break the 10 up and write that as 2 times 5 times whatever a is. And we're doing that here because we want to make something that is very clearly divisible by 2, something that is very clearly a multiple of 2. And now we're going to do this in the examples as well. So we're going to have, for 214, 2 times 5 times 21 plus 4, and 2 times 5 times 12 plus 5. Okay, so this gives us in our proof, and so this is where the arrow would be in our proof. Okay, so we've got our first bit here, the 2 times 5 times a. That part is clearly divisible by 2 because we have 2 times something. All right, now from our examples, we have 2 times 5 times 21 and 2 times 5 times 12. And then we get our test number b. That is our second part over there. So there is our second part, our second arrow. I hope the first one worked. And that gives us our test number b, which from our examples are 4 and 5. All right, continuing in our template, we're ready to use the divisibility lemma. N is divisible by 2. In this case, it's 2 because we're doing the divisible by 2 test. That's if and only if b, our test number. Got a little reminder there. That's what we have. If and only if b is divisible by 2. Again, that 2 is because we're doing the divisible by 2 test. And that's true if and only if the last digit, which in this case is b, is 0, 2, 4, 6, or 8. And we know that because if we're talking about a single digit number, when we pull off the last digit from our number, we're talking about a single digit. Well, which of our single digits are divisible by 2? That's 0, 2, 4, 6, or 8. And we could think about that as getting that from skip counting, those sorts of things. Now going back to our examples, 214 is divisible by 2 if and only if 4 is divisible by 2. So, yes, it is divisible by 2. And 125 is divisible by 2 if and only if the 5, which is our test digit here, is divisible by 2. But 5 is not divisible by 2, so 125 is not divisible by 2. Now, just as a note, the steps that we used in this proof work when we're proving a divisibility test that checks the last digit. So for example, the divisibility test by 5, the divisibility test by 10, both of those also, you determine whether the number is divisible by that by looking at that last digit. And you get the opportunity to do that in your homework. So your steps when you go through and do this in the homework should look a lot like these, but you're going to make the adjustment. Instead of 2s, you're going to have 5 or a 10 as you go through. So here we continue with the divisible by 4 test. So a whole number n is divisible by 4 if and only if its last 2 digits are a number that is divisible by 4. So following the same sorts of steps as we had before, by place value, any whole number n can be written as n equal 100a plus b, where b is the last 2 digits. And as we go through, I'm also going to do the examples off to the side, one that is divisible by 4 in blue and one that is not in red. All right, so we're going to work with 316 and 526. And so first we're going to separate out the test digits. So for 316, we're going to pull off the 16, and our place value experience tells us that means we're going to have a number that has 2 zeros at the end plus those last 2 digits. So we're going to have 300 plus 16. And then for 526, that's going to be 500 plus 26. And we're going to rewrite them in the form we've got in the proof, which is 100 times 3 plus 16, and 100 times 5 plus 26. And now we're going to keep going. We want to rewrite the 100 times a as something that is clearly divisible by 4. In other words, something that is a multiple of 4. So we're going to factor the 100 into 4 times 25. So we get 4 times 25 times a. We're going to do this for example numbers as well. So that's 4 times 25 times 3 plus 16 for 316. And 4 times 25 times 5 plus 26 for 526. So back to our algebraic proof here. This gives us 4 times 25 times a, and so it's divisible by 4 because it's clearly a multiple of 4. So we've got our arrow matching that part up there. And from our examples, we have 4 times 25 times 3 and 4 times 25 times 5. And then we also get our test number, and our test number is b because that's the second part that we have split off in the sum. And in our examples, our test numbers are 16 and 26. Continuing with the divisibility lemma, we're just applying it now. Our number n is divisible by 4. 4 in this case because we're looking at the divisible by 4 test. That is true if and only if our test number, b, is divisible by 4. And this is what the divisibility lemma does for us. It allows us to go from the larger number down to looking only at a smaller number. And our criteria here for b is that the last 2 digits are a number divisible by 4. So how do we know if b is divisible by 4? Well, if those are divisible by 4, then that works. So 316 is divisible by 4 if and only if 16 is divisible by 4, which is true. 526 is divisible by 4 if and only if 26 is divisible by 4, and it is not. So 526 is not divisible by, that should be 4. All right, moving on. we are now ready to, just one thing before we go on. So those steps in the proof work for proving divisibility tests that check the last 2 digits. And you can also adapt this for moving on and looking at something like the divisible by 8 test, where we're checking the last 3 digits, which you guys will get to do in your homework. And I know you're super excited about that. Okay, now we get to the divisibility test for 3 and 9, which you guys have probably heard before. They're fun. I really like these, but they're sort of a different style than the other ones. A number is divisible by 3 if and only if the sum of all of the digits in the number is divisible by 3. And same thing for 9. A number is divisible by 9 if and only if the sum of all of the digits in the number is divisible by 9. All right, we're going to prove that. So divisible by 3 test, we're going to do this proof only for 3-digit numbers. We could extend it more, but this gives you the idea of what you would have to do. And then in the homework, you get to do this for 9-digit numbers, for divisible by 9 with 4-digit numbers. But right now, we're just going to focus on how to prove this for 3-digit numbers. So we're going to start out, we're going to write a 3-digit number n as ABC. So A would be the number in the hundreds place, B is the number in the tens place, C is the number in the ones place. And then we're going to write that in its expanded form as 100A plus 10B plus C. Now as we go through this proof, I'm also going to do those examples alongside one in blue, one in red for divisible, not divisible, so you can see how this really works out. So we start with n. 100A plus 10B plus C, that's our expanded form. We're going to look at 732 and 235. So 732 in its expanded form, we would start out with 700 plus 30 plus 2, which we can rewrite as 100 times 7 plus 10 times 3 plus 2. With 235, that's 200 plus 30 plus 5. So that would be 100 times 2 plus 10 times 3 plus 5. All right. Now we get to a little bit of trickery here, but remember our goal is to figure out a part of n, our entire number here, that is clearly, easily a multiple of, in this case, 3. Well, 100 is not, but 99 is, and 100 is 99 plus 1. So we're breaking the 100 up into 99A plus A. And then we're going to look at 10B. 10 is not divisible by 3, but 9 is. So we're going to break the 10B up into 9B plus B. All right, now we're going to do that with our examples. So 100 times 7, we're going to break it up into 99 times 7 plus 7. And then 10 times 3 to 9 times 3 plus 3. We're going to do the same thing with 235. We get 99 times 2 plus 2, and then 9 times 3 plus 3. Now we're going to do a little bit of regrouping. We're going to group the 99A plus 99B together, and then the A plus B plus C together. We're doing that in part because the 99A plus 9B, that is going to be the part that we can rewrite as clearly a multiple of 3. And then the A plus B plus C, that is the sum of the digits in our number, and that is what we have to test to figure out whether the whole thing is divisible by 3. So now we're going to do rewriting in our examples. So we have 99 times 7 plus 9 times 3, and then plus 7 plus 3 plus 2. And with 235, 99 times 2 plus 9 times 3, plus 2 plus 3 plus 5. And then we notice that with the 99A plus 9B, we can factor out the 3, so we get 33A plus 3B. And then we still have our A plus B plus C on the end. And we can do the same thing with our examples. We get 3 times 33 times 7 plus 3 times 3, and that's just pulling a 3 out of those first 2 terms. And then with 235, we pull the 3 out of the first two terms, and we get 3 times the quantity, 33 times 2 plus 3 times 3. All right, so this gives us 3 times 33 times A plus 3B. It's right in here. And so it's divisible by 3 because it is clearly a multiple of 3. And from our examples, we see what we have peeled off there, just that individual part. And then our test number, so our test number in this case is the other part that was left over, the a plus b plus c. And with our two examples, we have 7 plus 3 plus 2, and then 2 plus 3 plus 5. Now by the divisibility lemma, again, this is where we're applying it, our whole number n is divisible by 3 if and only if the test number a plus b plus c is divisible by 3. So that is the same as saying the sum of the digits in the number is divisible by 3. So we're going to apply this to our two numbers. 732 is divisible by 3 if and only if 7 plus 3 plus 2, which is 12, is divisible by 3. So 732 is divisible by 3. And then if we look at 235, that is divisible by 3 if and only if 2 plus 3 plus 5 is divisible by 3. And when we add those together, 2 plus 3 plus 5 is 10, that is not divisible by 3. So 235 is not divisible by 3. Now, you're going to have to adapt this proof in the homework for divisible by 9. But you can see in here, there were lots of places where we had 9s, so it would be easy to pull 9 out instead of a 3 where we need to. So keep that in mind when you get to that in the homework. All right. Now we get to the very last part, which is divisibility test for 11. So this is phrased differently. It's a different kind of test that we have to do. I'm going to tell you how to phrase in two different ways. The first one is how it's phrased in the book. A number is divisible by 11 if and only if the number formed by taking the sum of the odd position digits minus the sum of the even position digits, if and only if that is a multiple, either positive, negative, or 0, of 11. And when we talk about the position number of a digit, that's counted starting from the right of the number. So the ones digit would be the first position, tens would be second position, hundreds would be third position, and so on. But another way to phrase this is that a number is divisible by 11 if and only if the number formed by adding and subtracting alternating digits is a multiple of 11. So you just take the first digit all the way on the left, you subtract the second one, you add the third one, you subtract the next one, and so on. That's a little simpler to do, I think. All right, we're going to apply this in some examples. First, we're going to determine whether the number is 83,821 is divisible by 11. And you should go ahead and pause and just work this out for yourself and then continue. But what we're going to do, I'm going to use that second formulation, and we're going to take 8 minus 3 plus 8 minus 2 plus 1, and we're going to see what we get. So that's, notice again, that's just alternating, starting with the 8 at the beginning, subtracting the next one, adding the next digit, subtracting the next one, and so on. And when we do this, we get 12, which is not a multiple of 11. So 83,821 is not divisible by 11. Next example, 112233. So we're going to have 1 minus 1 plus 2 minus 2 plus 3 minus 3, which gives us 0, which is a multiple of 11. It's multiplied by 0. So 112233 is divisible by 11. 9251. We're going to have 9 minus 2 plus 5 minus 1. We compute that, and we get 11, which is a multiple of 11. So 9251 is divisible by 11. And then we get 391,856,322. And I'll just say here at this point, in these examples and what you have in the homework, I have not put commas in to represent the separations with place value, simply because when I've done that in the past, people have thought I was giving a list of numbers instead of just using the comma for place value purposes to make it easier to look at. But that's why it's happening here. That's why I have all the numbers shoved together instead of separated with commas, which would make it easier to look at, but not necessarily easier to compute. And now moving on with our divisibility by 11 test, we get 3 minus 9 plus 1 minus 8 plus 5 minus 6 plus 3 minus 2 plus 2. and we end up with negative 11, which is a multiple of 11. So 391,856,322 is divisible by 11.